of like all the complex numbers. So all complex numbers. And complex numbers like encompass every single number that we will ever work with. And even some that we won't work with in this class. So imaginaries are numbers are complex numbers, real numbers are complex numbers. So complex numbers, it's like the biggest set of numbers that like holds everything else. So of course we're not really going to work with imaginary numbers in this class. So like the size that I make these things has nothing to do with like how many things are in the set of numbers. I'm just giving myself more room to write in part of it. So then this is going to be the set of real numbers. And then within the set of real numbers, so real numbers are essentially all numbers that don't contain the square root of a negative. So the only way we get an imaginary number is by trying to take the square root of a negative. So everything on the left side there is just every single number that we've ever heard of or looked at or seen that doesn't involve the square root of a negative. And then within that is this set of numbers that we call the rational numbers. And the rational numbers are, well, we've been working with rational expressions, right, which are just fractions. So same deal here. Rational numbers are numbers that can be written as fractions. And really, these are the numbers that we've worked with basically all our life. They actually hold more than it sounds like they do. So every single decimal so repeating decimals, so that repeat after, like in a pattern, you know, where you can draw like the line over the digits, those can all be written as fractions. Terminating decimals, so decimals that stop after like some number of digits, can all be written as fractions. So rational numbers contain all the whole numbers, all the integers, all the fractions, all the decimals that repeat, and all the decimals that end. Which means that this set of numbers right here, all this stuff in here, which we call the irrational numbers, those are all the decimals that never ever repeat in any pattern, and they never ever end. So we don't actually end up seeing a lot of these because they're impossible to write down in their exact form, right? We'd have to have an infinite amount of paper and an infinite amount of time, because we'd have to be writing for an infinite forever, because they never end, they never repeat, so we can't put like a bar on top. So because of that, the only way we have to represent irrational numbers in their exact form is just by using some sort of a symbol, right? So any other thing is just an approximation. So if we write a decimal down for an irrational number, we've really just approximated it. So everybody's favorite irrational number is pi. And that's the symbol we use to represent pi in its exact form. Yes, there's an approximation of pi, right? It's like 3.14 something, something, something. But that's just an approximation. And it seems somewhat silly for us to like bicker over like those like few hundredths, you know, and say like, why isn't it just 3.14, right? It's close enough. But if you think of it like in the grand scheme of things, as far as actually using numbers in real life, like if we're building, let's say, a gym, and the first calculation we do, we have to round, and then we use that in every single other calculation to calculate every single other measurement, then every time we do a calculation with that rounded number, we get a little further away from the exact value. So if we round a number and it's off by like a tenth, then when we multiply that number by 2, now we're off by 2/10, right? Like, so it all compounds, and then at the end of it all, roofs fall down.
That's why our gym collapsed.
Exactly. Somebody rounded in an intermediate step. But, so we like to be able to write these numbers in their exact form all the way up until that very last step when we're actually ready to, like, make a measurement, right? And then, of course, it makes sense to, like, round to some place value because we have to be able to actually measure it out. But so it's not that like we're just being picky about like, oh, everything has to be exact. It's just that in practice, we use these numbers for things, right? We use them in multiple steps of problems. And so we want to wait until the very, very end until we do any rounding so that we're not compounding that estimation more and more and more every time. So we have to use symbols to represent these irrational numbers. We've all seen pi. In a couple weeks, we will talk about e is another irrational number that's used really often. And then the most often, or the ones that we use most often are radicals. So every square root, cube root, fifth root, whatever, that does not give you a whole number. So all the ones we talked about yesterday, we just got whole numbers, right? When we took like the square root of 9, it was 3, because 3 squared is 9. But if what's under the radical isn't a perfect square or a perfect cube or a perfect fourth or whatever our index is, then that's an irrational number. So like the square root of 2 is an irrational number because there's no whole number you can square to get to. It's some really nasty decimal that goes on forever and never repeats. And so just like with pi and e, we have to use a symbol to represent it. And like this is just the symbol that represents the number that can be squared to get 2. So you sort of have to get comfortable with having these symbols that look like numbers because they have like numbers in them. And understanding that like the square root of 2 really isn't the same as the number 2 at all. It represents a completely different number, but it's just a symbol that we use to represent that value so that we can use that in its exact form all the way up until we absolutely have to round it for some reason. So because we're using symbols to represent these numbers, we would like to make those symbols as concise as possible. So we have ways of breaking these down so that we can write them in as simple a form as we can. And that's what we're going to work on today, is simplifying these radicals where we can't actually get a whole number just by taking the square root of something or the cube root. We're going to start with square roots. We'll do a couple cube roots, but we're going to focus mostly on square roots because that's what you'll use the most. Let's start with, say, so the instructions for all of these problems are going to be to simplify. And I'm not trying to write that every single time because, like I said, I'm writing like a third grader. So simplify are the instructions for every single example I'm about to do. The first example we'll do is just the square root of, let's say, 50. So this is a fairly simple one, which honestly we could do a different way. It's a little easier, but we're going to do it kind of a long way so that we can extend that to more complex ones that have more factors in them. So the way that we simplify is we start with the prime factorization of the radicand, so the number under the radical. So we can do a factor tree. And then we're always going to write these in exponential form because we talked yesterday about how to take the square root of something raised to a power. We just multiply that exponent by a half, right? Or divide it by 2. So if we have like the square root of x to the n, that's the same as x to the n divided by 2. So if we can write everything in exponential form, then we can take the square root just by dividing our exponents by 2. So we're going to say this is the square root of 5 squared times 2. And then as long as everything is multiplication or division, we can break these up and put them back together as much as we want. So everything works out really nicely with radicals if we have multiplication and division. If we have the square root of like 5 squared plus 2, then it's no longer really fun and easy to just break things up and put them back together. But as long as everything is multiplication and division, we can break these up into 2 radicals, put them back together into 1 radical, whatever we want. So I'm going to call this the square root of 5 squared times the square root of 2. And then we're going to go through factor by factor and take the square root of anything we can take the square root of. So anything that has an even exponent, we can divide that exponent by 2. So the square root of 5 squared is just 5. And then the square root of 2 is just the square root of 2, because there's nothing I can do to simplify that further. I can't take the square root of 2 because it's an irrational number. I don't have any exponent there that I can divide by 2. And so this is just the square root of 2. And so our final answer is just 5 times the square root of 2. So let's do something with a few more factors. How about the square root of I want to change it to 8. It'll be so much more fun. So again, we're going to start with that prime factorization. So we have 828. That's 2 times 4, 14. Which is 2 times 207, which is 3 times 69, which is 3 times 23. Do we have their calculator out? Can somebody just punch in like 23 times 3 times 3 times 2 times 2, just to make sure I didn't mess that up at all? I think that's all true. Okay. So then I'm going to group these. So I know that to take the square root, I want to divide the exponent by 2. So I'm going to group these into groups that have an even number of factors. So I've got 2 factors of 2, 2 factors of 3, and then 1 factor of 23. So 2 squared times 3 squared times 23. So I want the square root of 2 squared times the square root of 3 squared times the square root of 23. So the square root of 2 squared is 2, the square root of 3 squared is 3, and the square root of 23 is just the square root of 23. And when we have multiple factors like this, we can now take everything that's not inside the radical and make that our coefficient, and then everything that is inside a radical and make it a single radical. So we'll call this 6 times the square root of 23. We can extend this same idea to variable factors. So if we have x raised to a power, it's actually kind of simpler because we don't have to worry about breaking the number down with prime factorization, because like if you have x raised to a power, the only factors in there are x, right? So let's say I want to simplify the square root of x to the 16th. What would that be? Yeah, it'd be x to the 8th. When we see that 16, it's really tempting to think 4, right? Because the square root of 16 is 4. But remember, we're not taking the square root of the number 16 here. We're taking the square root of 16 factors of x. So if you imagine all those 16 factors of x lined up, we can do 8 factors of x times 8 factors of x. So if we kind of split that big line of x's in half, then we can see that 16 factors of x is just 8 factors of x times itself. So again, dividing that exponent in half gives us 2 factors that are the same, which is a perfect square. So we have x to the 8th is the square root of x to the 16th. So just be really careful to differentiate between how we treat exponents and then how we treat actual numbers, because it's different. And then how about the square root of x to the 9th? Well, it's not going to be x to the 3rd, right? Because we just talked about that.
X to the 9 over 2.
Yes, that is true. It is equivalent to x to the 9 over 2. For our purposes today, we want to simplify these radicals as radical expressions. So we don't want any rational exponents like we had yesterday. So those have their place and they're useful in some situations. But when we're just working with the radicals as radicals, we don't want to have any fractional exponents floating around. And so what we have to do, because you're right, like we can't if we line up 9 factors of x, we could break it into like 5 factors of x or 4 factors of x, but the only way to get like an even number in each group would be to split one of them in half, right? So we're going to break off 1 factor of x here so that we have an even number of factors and then an extra factor of x. So every odd number we can write as an even number plus 1, right? So x to the 9th is the same as x to the 8th times x. So we're just writing our 9 factors of x in a different way. And so then that is, we have the square root of x to the 8th times the square root of x. What's the square root of x to the 8th? So x to the 4th times the square root of x. So let's put this all together. Pick a number that's actually going to work. Square root of 432. 15th y to the 12th. So this looks a bit more complex than what we just did, but remember that we can break this up as much as we want. So we can break it into individual factors. And if we write this as the square root of 432 times the square root of x to the 15th times the square root of y to the 12th, well, then we kind of just have like 3 little problems that are exactly the same as the ones we just did, right? So we're going to break each of those up individually, and then we'll put it all back together at the end. So we'll start with that prime factorization of 432. So 216, which is 2 times 108, which is 2 times 54, I'm running out of room, which is 2 times 27, which is 3 times 9, which is 3 times 3. So I want to group this into factors, or groups that contain an even number of factors. So we're going to do 4 factors of 2, 2 factors of 3, and then 1 extra factor of 3, right? Because we want all our exponents to be even. So if we have an odd number of factors of 3, just like we did with that x to the 9th, we're going to write it as something with an even exponent times 1 extra factor of 3. So we have the square root of 2 to the 4th times 3 squared times 3. And then x to the 15th, that has an odd exponent, right? So we're going to do the same thing we did with our x to the 9th. We're just going to break 1 factor of x off. And it's always just going to be 1 factor, right? Because every odd number has an even number that's 1 less than it. So like there'd be no reason for us to write this as like x to the 10th times x to the 5th or something like that, because x to the 5th still contains like some perfect squares, some x squareds in it. So we just want the 1 factor of x. And then y to the 12th has an even exponent, so we'll just leave it alone. So breaking these up gives me 2 to the 4th, or the square root of 2 to the 4th times the square root of 3 squared times the square root of 3 times the square root of x to the 14th times the square root of x times the square root of y to the 12th. I know this might seem a little bit tedious, but honestly the most common mistake in these guys is like losing track of like what you've taken the square root of and what you haven't taken the square root of and what's inside the square root and what's not inside the square root. So that's the reason I break it down like into individual factors, because then I can just go through factor by factor and take the square root. Another thing that helps with avoiding mistakes in that respect is only taking the square root in one step. Like at the beginning of this problem, we could have been like, oh, that's a perfect square. The square root of y to the 12th is y to the 6th, and like done it up there, but then we had to work with all these other factors. And so then it's easy to get mixed up of like what you have taken the square root of and what you haven't. So that's why I just carried that with me, and now I'm going to take the square root of every single factor at the same time instead of trying to like mix and match what I have and haven't worked with yet. So you want to break everything down completely and then just go through factor by factor. Honestly, I've never seen people make mistakes if they actually write it all out. The only time I see mistakes in these problems is when you start skipping steps and losing track of what's under the radical and what's not under the radical, and people, the whole inside-outside thing is sort of arbitrary. But if we just go through factor by factor, I never see errors with this. So the square root of, that is not a challenge, by the way. Don't try to get it wrong, just to prove me wrong. What's the square root of 2 to the 4th? Yeah, so I'm going to write as 2 squared, and then we will write as 4 here in a minute. Square root of 3 squared? 3. Square root of 3 is just the square root of 3. Square root of x to the 14th? X to the 7th. Square root of x. Very good. And then the square root of y to the 12th? Very good. So that's the other place where we want to be careful is as far as when you have a radical and when you don't. So the radical symbol is like an operation, just like addition or subtraction or what have you. And so when you use it, you use it up, right? So if you take the square root of 2 to the 4th, to get 2 squared, you no longer have a radical symbol because you use the radical symbol to take the square root. Whereas when we have the square root of 3, we can't take the square root of 3, and so we still have to have our radical symbol because we haven't used it to actually take the square root of anything. So that's how you want to tell if you're going to have a radical or not. It can get confusing. And again, that's why we just go through factor by factor, because it's a lot easier to tell what's inside and outside the radical one factor at a time than if you look at all of it at once and try to move them all around. But now that we have everything, we've taken the square root of everything, now we're going to just rearrange to make this a little bit more compact. So we're going to take everything that's not under the radical and make that our coefficient. So 2 squared times 3 is 12. And x to the 7th times y to the 6th. And then we could take all the factors that are under the radical and just put them under a single radical. So we have the square root. Oh, I used this but didn't underline it, sorry. Then we have the square root of 3 and the square root of x, so that's the square root of 3x. And then we're done. And if you're not already having a ton of fun, we can do this with cube roots too. So if I'm going to simplify a cube root, what do I want to divide my exponents by? Yeah, right? Because we talked yesterday about how that index becomes the denominator of the rational or fractional exponent. So whenever you're taking the cube root of something, you're dividing your exponent by 3. So we're going to do the same thing we did here, except instead of grouping our factors into even numbers of factors, we're going to group them into numbers of factors that are divisible by 3. So write them with exponents that are divisible by 3. So let's simplify. Where are you? The cube root. Uh, 144 x to the, let's see over here, 7th, y to the 11th. So one thing you want to be really careful of is when I see a radical and I see a perfect square like 144, which is 12 squared, I really want to write a 12, right? The square root of 144 is 12, woo! But you want to be careful that you pay attention to your index, because remember, we're not taking the square root, we're taking the cube root, and 144 is not a perfect cube, even though it is a perfect square. So we want to break that down into all its factors. We have 144, which is 2 times 72, which is 2 times 36. 2 times 18, which is 2 times 9, which is 3 times 3. And then our goal here is to group factors into groups that have where the number of factors is divisible by 3. So I'm going to take 3 factors of 2, and then the rest of them are just kind of on their own. So we have the cube root of 2 to the 3rd times 2 times 3 squared. And then I have 7 factors of x. What is the largest exponent I can use that is a multiple of 3? So I'm going to write my 7 factors of x as 6 factors of x times 1 more factor of x. And then if I have y to the 11th, what's the largest exponent I can use that's going to be divisible by? Yeah, it's 9. So I'll write that as y to the 9th times y squared. And so I want to take the cube root of 2 to the 3rd. And this is a place where you can cheat a little bit as far as like skipping a step. If I look at that 2 times 3 squared, like I know I'm not going to be able to take the cube root of either of those. So I'm just going to not break that up at all. And then I have the cube root of x to the 6th times the cube root of x times the cube root of y to the 9th times the cube root of y squared. So what's the cube root of 2 to the 3rd? Just 2. 2. And then the cube root, like I said, like 2 times 3 squared, I'm not going to be able to take the cube root of anything, so I don't have 3 factors of anything. So I'm just going to multiply that 2 times 3 squared to give me a nicer number. So this is the cube root of 18. And then what's the cube root of x to the 6th? Squared. And then times the cube root of x. And the cube root of y to the 9th is y to the 3rd. Again, we're just dividing those exponents by 3. And then times the cube root of y squared. So we'll take everybody that is not inside a radical. It gives me 2x squared y to the 3rd. And then times the cube root of, we have 18x and y squared. So 18x y squared. And one thing you might notice, like when we get to our final answer, as far as exponents that you can have inside the radical, you'll always end up with exponents that are less than your index, or else you could have broken it down further, right? So if we're taking a square root, we shouldn't have any exponent. Well, I mean, we have exponents of 1, but we don't write the exponents of 1, right? So in our final answers, we'll never have exponents greater than 1 when we're taking the square root. Whereas when we're taking the cube root, we can have something squared, because that's still less than 3 factors of y, right? So we can't break it down anymore. But if we have something to the 3rd or something higher, then that contains something to the 3rd that we could have taken the cube root of. So like if we were taking the 6th root, we can have, in our final answer, we can have exponents up through 5, but none that are 6 or greater. So that's a good just kind of thing to check at the very end. Make sure all your exponents are less than your index to make sure that you've actually taken out everything that you can. Next, we're going to talk about multiplication and division. And the good news about that is that it's really exactly the same thing. If we're multiplying or dividing radical expressions, we're going to mush them into 1 and then do the same exact thing to simplify. So the key, though, is that mushing them into 1 part. Because if we don't write it as a single radical, then we'll never be able to actually fully simplify it down to like a coefficient and 1 radical. So whenever you multiply or divide radical expressions, always write as a single radical first. So if we have where'd it go? The square root of 20x to the third y to the fifth times the square root of 8x to the 10th y. The first thing we want to do is just write this as just one radical. So I'm going to put everything under one radical and combine things as necessary. So I'm not actually going to do 20 times 8. I'm just going to write it as 20 times 8. And the reason for that is that, like, the next thing I'm going to do is the prime factorization, right? So if I was doing the prime factorization of 160, I could be like, oh, 160 is 20 times 8, and then break down 20 and 8. So I might as well just leave it as 20 and 8 and break down 20 and 8 from the start instead of, like, getting a bigger number. I mean, 160 is not that bad, but we could end up with a really nasty number, so we might as well just break them down individually and combine all the factors than actually get a big number and try to break that down. But I do want to count up all the factors of x and y. So we have x to the 13th and then y to the 6th. And now this problem is exactly like the ones we've been doing, right? We have a single radical. We're going to do prime factorization and write everybody with an even exponent. So when I have a product, I like to do like 2 separate factor trees, but then count up all the factors at once. So we'll do 2 times 10, 2 times 5, 2 times 4, 2 times 2. So then I see that I have like 4 factors of 2, and then a factor of 5 and a factor of 2. So you can group all of those together to get your group of an even number of factors, and then whatever leftovers you have. So we have the square root of 2 to the 4th times the square root of 2 times the square root of 5. So I'm just separating those factors as I go rather than writing all the factors and then separating them. That's a step that you're welcome to skip because it's not a step that has anything to do with actually taking the square root. It's just we're just breaking up factors. So then that x to the 13th, well, that's 12 factors of x and 1 factor of x. So we'll write it as the square root of x to the 12th times the square root of x. And then y to the 6th has an even exponent already, so we'll leave it on. And now we'll take our square root. So the square root of 2 to the 4th is 2 squared. These I'm not going to be able to take the square root of, so I'm going to go ahead and combine them and call that the square root of 10. And then the square root of x to the 12th is x to the 6th. The square root of x is just the square root of x. And the square root of y to the 6th is y to the 3rd. And then we'll put it all together. Let's see, we have 4 x to the 6th, y to the 3rd, and then the square root of 10x. Is this fun? It's kind of like a puzzle, right? You need to break it all down. That's what I do in my free time. We can do the same thing or use the same idea with division, and it's actually even more useful to put it into a single radical because we can simplify our fraction, which then gives us like smaller numbers and less factors to work with. So, for example, if I want to simplify it, so the square root of 160 x to the 4th y to the 3rd over the square root of 40 x y to the 9th. So the first thing I'm going to do is just write one big radical. And put that whole fraction under it. So 160 x to the 4th y to the 3rd over 40 x y to the 9th. So now what I want to do is simplify that fraction. So this has nothing to do with the square root at this point. I'm looking at just this, and that's similar to like an expression that we simplified on Monday, right, with our exponent rules. So all I'm going to do is cancel common factors here. We still have our square root because we haven't done anything as far as taking the square root of anything. So 160 divided by 40 is like, what, 4? And x to the 4th divided by x, we can use our quotient rule there. That's just x to the 3rd. And then y to the 3rd divided by y to the 9th. Well, if I cancel 3 factors of y, where are my leftover factors going to be? In the bottom, yeah. So, I mean, you could use the quotient rule there and then deal with the negative exponent. But if all of your exponents are positive, I think it's easiest just to like think about where the extra factors are rather than getting like negative exponents involved. If all the exponents aren't positive, that method kind of goes out the window. But here we can just kind of look at it to figure it out. So now we're just going to do the same thing we did with the product. We're going to go through and take the square root piece by piece. So we have the square root of 2 squared, that's my 4. And I mean, in this one, really, you could just do the square root of 4 because you probably know the square root of 4, but just to be consistent. And then that x to the 3rd, I'm going to write as x squared times x. So this is the square root of x squared times the square root of x. And then over the square root of y to the 6th, which has an even exponent, so I don't need to break anybody off. And just make sure that you're keeping everything in the numerator, like whatever was in the numerator stays in the numerator, whatever is in the denominator stays in the denominator as you do this. So the square root of 2 squared is 2. The square root of x squared is x. The square root of x is the square root of x. And the square root of y to the 6th is y to the 3rd. So we have 2x root x on top divided by y to the 3rd, which was a lot easier than simplifying the radical on top and the radical on the bottom separately and then having to like cancel factors, right? So it's really important. It's probably the one thing people forget the most on these is to just make everything a single radical, and then you can break it up afterwards. But if we simplify that fraction first, then we just eliminate a lot of work for ourselves with having like a ton of factors to deal with. So that's about everything for today. Tonight you just have my math lab.